There's a moment in a physicist's life when everything you've been working on, every calculation, every sleepless night wrestling with equations, comes down to a single encounter. For me, that moment came in 1947 at Princeton. I was going to present my work to Einstein, not write to him, not send him a paper, stand in front of him and explain a completely new way of understanding quantum mechanics and electrodynamics. Let me tell you what led to that moment, because the physics itself is what matters, not the drama of meeting famous people. I'd been working on a problem that had been tormenting physicists since the early days of quantum mechanics. When you try to calculate what happens when an electron interacts with light, when it absorbs or emits a photon, the mathematics gives you infinity, not a large number. Infinity. The electron's interaction with its own electromagnetic field produces infinite energy. The self-energy problem, we called it. This wasn't a minor inconvenience. This was the central equation of quantum electrodynamics, QED, the theory that should describe how light and matter interact. And it didn't work. Every time you tried to calculate something precisely, you got nonsense. Infinities everywhere. The theory predicted that an electron should have infinite mass and infinite charge. Obviously wrong. We measured the electron's mass, we measured its charge. They're finite. Other physicists had tried various tricks. Hendrik Kramers suggested that maybe the infinities could be absorbed into the definitions of mass and charge, what we now call renormalization. But nobody had a systematic way to do the calculations. The mathematics was a mess. You couldn't make predictions. You couldn't compare theory to experiment beyond the crudest approximations. I approached this problem differently. I didn't start with the conventional formalism, the Hamiltonian, the field operators, all that machinery from the textbooks. I went back to a more fundamental question: what is actually happening when an electron interacts with a photon? In classical physics, we have something called the principle of least action. If you want to know how a particle moves from point A to point B, you don't track its position at every instant. Instead, you consider all possible paths the particle could take, assign each path a number called the action, and the actual path is the one where the action is minimized. Or more precisely, stationary. It could be a minimum or a maximum or a saddle point. This principle is beautiful because it's global. You don't need to know the force at every point along the path. You just need to know the endpoints. Calculate the action for each possible path, and find which path makes the action stationary. For a free particle, that's a straight line. For a particle in a gravitational field, it's a parabola. The mathematics gives you Newton's laws, but the conceptual framework is completely different. Now, here's what I realized. In quantum mechanics, we shouldn't just consider the one path where the action is stationary. We should consider all paths, every possible trajectory from A to B, no matter how wild or zigzagging, and we should assign each path a quantum amplitude, a complex number whose phase is proportional to the action of that path divided by Planck's constant. This idea wasn't entirely new. Dirac had mentioned something like it in a paper, but I worked out the mathematical details and showed that you could derive all of quantum mechanics from this path integral formulation. The Schrödinger equation, the Heisenberg uncertainty principle, everything. It all followed from summing over all possible paths. But the real power came when I applied this to quantum electrodynamics. Instead of thinking about fields and operators, I thought about particles and their trajectories through space-time. An electron starts here at this time, ends there at that time. A photon is emitted here, absorbed there. Draw all the possible ways this could happen. Each diagram represents a term in the mathematical expansion. These diagrams, what people now call them by my name, though I always just thought of them as a calculational tool, made everything visual and concrete. You could see what was happening. An electron traveling along, emitting a photon, recoiling, or two electrons exchanging a photon, or an electron emitting a photon, and then reabsorbing it. A virtual process that happens in the quantum foam of space-time. And here's the crucial part. The infinities were still there, but now I could see where they came from. They came from virtual processes where the electron emits and reabsorbs a photon with arbitrarily high energy and momentum. The contribution from these high-energy virtual photons diverged, went to infinity. But Kramers was right. You could absorb these infinities into redefinitions of the electron's mass and charge. The infinite self-energy could be subtracted away if you define the physical mass as the measured mass, not the bare mass that appears in the original equations. Same for charge. After this renormalization, all the infinities canceled out, and what remained were finite, calculable predictions. I worked out the rules for doing these calculations systematically, how to draw the diagrams, how to translate each diagram into a mathematical expression, how to handle the virtual particles, how to renormalize consistently, and most importantly, I could now calculate things that had never been calculated before. For example, the magnetic moment of the electron. Classically, a spinning charged particle should have a magnetic moment proportional to its angular momentum. The proportionality constant is called the G factor, and classically it should be exactly 1. But the Dirac equation predicted it should be exactly 2. Experiments showed it was close to 2, but not exactly 2. The discrepancy was tiny, about 1 part in 1,000, but it was real. Using my methods, I could calculate the correction. The electron emits and reabsorbs virtual photons. These virtual processes slightly modify its magnetic moment. I worked through the calculation, summing over all the relevant diagrams, doing the integrals, renormalizing the infinities. The correction came out to be alpha divided by 2 pi, where alpha is the fine structure constant, about 1 over 137. This gave a G factor of 2 times the quantity 1 plus alpha over 2 pi. Numerically about 2.0023. The experimental value at that time was about 2.002. The agreement wasn't perfect, the experiments weren't precise enough yet, but it was close. Real close. And it was a genuine prediction, not a fit to data. This was the calculation I was going to present at Princeton, not just to Einstein, but to a whole room of physicists. Oppenheimer had organized a small conference to discuss the new developments in quantum field theory. Several people had been making progress on the renormalization problem. Schwinger had his own formulation. Tominaga in Japan had developed similar ideas independently. But my approach was different, more visual, more intuitive, I thought. I was nervous. Not because of Einstein specifically, but because I was about to present a completely new way of doing calculations in quantum mechanics, and I wasn't sure anyone would understand it. The diagrams seemed obvious to me, but would they seem like physical nonsense to everyone else? Was I just inventing a fancy bookkeeping scheme, or was I revealing something about how nature actually works? The meeting was in the basement of Palmer Physical Laboratory. There were maybe 20 people there. Einstein sat in the front row. He was 68 years old then. He'd already spent more than 20 years trying to unify gravity with electromagnetism, working on his unified field theory, increasingly isolated from the mainstream of physics. He didn't believe in quantum mechanics, not in the sense of accepting that nature was fundamentally probabilistic. He thought it was incomplete, that there must be hidden variables underneath giving the appearance of randomness. I started by explaining the principle of least action in classical mechanics. Then I showed how in quantum mechanics, you sum over all paths, not just the one with stationary action. Each path contributes an amplitude. The total amplitude is the sum. The probability is the absolute square of the amplitude. Then I moved to electrodynamics. An electron interacts with the electromagnetic field. In the conventional formulation, you have creation and annihilation operators for photons, field operators for electrons, interaction Hamiltonians. It's abstract. It's hard to visualize what's really happening. In my formulation, you draw space-time diagrams. Here's an electron world line. Here's where it emits a photon. Here's where another electron absorbs that photon. Each junction, each vertex where an electron emits or absorbs a photon, contributes a factor proportional to the electric charge. Each internal photon line contributes a propagator, a mathematical expression describing how the photon travels from emission to absorption. I showed them how to calculate the electron-electron scattering amplitude. Draw all possible diagrams, with 2 electrons going in, 2 electrons coming out, and photons being exchanged between them. There's the simplest diagram, 1 photon exchanged. Then there are more complicated diagrams, 2 photons exchanged, or 1 electron emitting and reabsorbing a photon before scattering, and so on. Each diagram corresponds to a term in a series expansion. The expansion parameter is alpha, the fine structure constant. Since alpha is about 1 over 137, the series converges quickly. The first term dominates. The second term is a correction of about 1%. The third term is about 0.01%. You can calculate to whatever precision you need. I explained the renormalization procedure. The bare mass and bare charge that appear in the original Lagrangian aren't the physical mass and charge we measure. They're related but not identical. The difference is absorbed by the infinite contributions from high-energy virtual processes. After renormalization, all predictions are finite and in terms of measured quantities. Einstein listened carefully. He didn't interrupt. I could see him following the argument, but I couldn't tell what he was thinking. His face was thoughtful, concentrated. When I finished the main presentation, I showed the calculation of the electron's magnetic moment. This was the real test, a prediction that could be compared with experiment. I wrote down the diagrams that contribute to the magnetic moment. The leading correction comes from one diagram. The electron emits a virtual photon, then reabsorbs it. The photon can have any momentum and energy, so you integrate over all possibilities. The integral diverges, gives infinity, but the divergence is the same type that gets absorbed into the mass renormalization. After subtracting the infinite part, what remains is finite, alpha over 2 pi. This was the first time anyone had calculated a radiative correction in quantum electrodynamics and gotten a finite, meaningful answer. Schwinger had calculated it too, independently, using his own methods. We got the same answer, which was reassuring. Different mathematical approaches, same physics. After I finished, there were questions. Several physicists asked about technical details, how to handle certain types of diagrams, whether the renormalization was unique, how many diagrams you needed to include for a given precision. These were good questions. They showed people were engaging with the method, trying to understand how to use it. Then Einstein asked a question. He wanted to understand how the path integral formulation related to the uncertainty principle. If you're summing over all paths, including paths where the particle has a definite position at every time, doesn't that violate uncertainty? Doesn't quantum mechanics forbid a particle from having a definite trajectory? This was exactly the right question to ask. It got to the heart of what the formulation meant physically. I explained that the uncertainty principle emerges from the sum over paths. It's not put in by hand. When you sum over all paths with their quantum amplitudes, the phases of most paths cancel each other out. Only paths near the classical path, the path of stationary action, contribute significantly. And the spread in those contributing paths is exactly what gives you the uncertainty relation. Let me be more precise. Each path has an action. The quantum amplitude for that path is e to the I times the action divided by h bar, where h bar is Planck's constant divided by 2 pi. Now, paths where the action differs by much more than h bar will have very different phases. Their complex amplitudes will point in different directions in the complex plane. When you add them up, they cancel. Only paths where the action is within about h bar of the stationary value contribute constructively the width of this bundle of contributing paths. This is what gives you the quantum uncertainty. For a particle with definite initial and final positions, the paths that contribute spread out over a region in space-time. That spreading is the uncertainty. The position-momentum uncertainty isn't a limitation on measurement. It's a consequence of how quantum amplitudes add up. It's built into the structure of the path integral. Einstein nodded. He seemed to accept that explanation, though I could tell he wasn't entirely satisfied. He had a deeper reservation about quantum mechanics itself, not about the mathematical consistency, which was clearly there, but about the physical interpretation. He believed nature should be deterministic underneath all this probability. The path integral, in his view, was probably just an efficient calculational method for a theory that was ultimately incomplete. I didn't agree, but I respected that he was asking the right kind of question, not about the mathematics, which was clearly consistent, but about what it all meant. What is really happening when an electron goes from here to there? Does it actually take all paths simultaneously, or is that just a mathematical device? I didn't have a definitive answer then, and I'm not sure we have one now. But the mathematics works. The predictions match experiment. That has to count for something. After the formal presentation, Einstein approached me. We talked for a few minutes in the hallway outside the lecture room. He said the approach was interesting, that it gave physical insight into the calculations in a way that the standard operator formalism didn't. He appreciated that you could see what was happening, electrons moving, photons being exchanged. But he remained unconvinced that quantum mechanics was the final theory. He thought there must be something deeper, some underlying deterministic structure that we hadn't discovered yet. I told him I didn't know if quantum mechanics was final. Maybe there was something deeper. But whatever that deeper theory was, it would have to reproduce all the predictions of quantum mechanics, because quantum mechanics worked. The predictions matched experiment to incredible precision. So even if there were hidden variables or some other underlying mechanism, the probabilistic structure of quantum mechanics would have to emerge from it. We couldn't just throw quantum mechanics away. We could only hope to understand it better. He smiled at that. I think he appreciated that I wasn't being dogmatic about it. Physics isn't about defending a position or believing the right doctrine. It's about following nature wherever it leads, even if it leads to places that make you uncomfortable. Einstein understood that better than almost anyone. His whole career had been about challenging accepted wisdom when the evidence demanded it. What mattered to me wasn't Einstein's approval or disapproval. What mattered was that the physics worked. The diagrams gave the right answers. The renormalization procedure was mathematically consistent. You could calculate the electron's magnetic moment, the Lamb shift in hydrogen, the rate of electron-positron pair production, all these effects that couldn't be calculated before. Over the next few years, the experimental precision improved. The electron's magnetic moment was measured more and more carefully. Every time the result agreed with the theoretical prediction to within experimental error. When higher-order corrections were calculated, diagrams with more virtual photons, more complicated structures, they agreed too. Eventually, the agreement between theory and experiment in quantum electrodynamics reached parts per billion. It became the most precisely verified theory in the history of physics. But that day at Princeton, we didn't know any of that yet. We just knew we had a new set of tools for calculating quantum processes. We had turned quantum electrodynamics from a theory that gave infinities into a theory that gave numbers that could be compared with experiment. Looking back, what was significant about that moment wasn't the meeting itself. It was what the physics represented. For 20 years, quantum mechanics and special relativity had been uneasy partners. Quantum mechanics worked beautifully for atoms and slow particles. Special relativity worked beautifully for fast particles and light. But putting them together in a consistent quantum field theory seemed impossible because of the infinities. The breakthrough came from taking the mathematics seriously but not literally. The infinities were telling us something. They weren't a sign that the theory was wrong. They were a sign that we were asking the wrong question. We were asking for the value of the bare mass and bare charge, quantities that don't correspond to anything we can measure. What we measure is the dressed mass and dressed charge, the particle surrounded by its cloud of virtual photons. Once you accept that the parameters in your theory need to be renormalized, that they're not directly observable quantities, the infinities go away and you're left with finite predictions in terms of things you can actually measure. This seemed like cheating to some people. Dirac never liked it. He thought a proper theory shouldn't have infinities that need to be subtracted away. But nature doesn't care what we think is proper. Nature uses renormalization. We know now that renormalization is more than a trick for handling infinities. It's telling us about the structure of physics at different scales. When you probe matter at very short distances, very high energies, you see different effective values of the coupling constants. The fine structure constant isn't really constant. It runs, it changes with energy. At low energies, it's about 1/137. At very high energies, it's larger. This running is a consequence of vacuum polarization, virtual particle loops, all the quantum effects that we renormalize away at any given energy scale. This insight, which emerged from trying to make sense of the infinities in quantum electrodynamics, eventually became central to our understanding of all fundamental forces. The strong nuclear force, the weak force, even the structure of what we now call the Standard Model, they all involve renormalization and running coupling constants. What seemed like a mathematical trick in 1947 turned out to be a deep feature of how nature works at a fundamental level. Einstein didn't live to see most of these developments. He died in 1955, still working on his unified field theory, still convinced that quantum mechanics was incomplete. I don't know if he would have changed his mind if he'd seen the success of quantum field theory in describing all the forces except gravity. Maybe he would have. Maybe not. He was a stubborn man in the best sense. He didn't change his mind easily. He needed convincing evidence, not just mathematical elegance. But what I learned from that encounter, and from the years of work that followed, is that physics progresses not by authority or consensus, but by calculation and experiment. It doesn't matter what Einstein thinks, or what I think, or what anyone thinks. What matters is what nature does. And you find out what nature does by making predictions and testing them. The path integral formulation, the diagrams, the renormalization techniques, these weren't just mathematical tools, they were ways of asking nature questions and getting answers. Every diagram is a question. Does this process happen? How strong is it? What's its probability? And nature answers through experiment. Yes, that process happens. Here's how strong it is. Here's the cross-section, the lifetime, the decay rate. The most profound thing I took from that work wasn't a specific result. It was an approach to physics. Don't get lost in formalism. Don't worship equations. Use mathematics as a tool to describe what's physically happening. Draw pictures. Visualize the processes. Think about what an electron is actually doing when it interacts with a photon. Then translate that physical picture into mathematics. Calculate. Compare with experiment. Revise if necessary. This approach served me well for the rest of my career. Whether I was working on liquid helium or parts and models or the weak interaction or quantum computing or teaching freshman physics, the principle was the same. Understand the physics first. The mathematics follows. Don't hide behind abstraction. Make the ideas concrete and visual whenever possible. That day at Princeton, I was a young physicist presenting to the great Einstein. But I wasn't trying to impress him. I was trying to explain how nature works. That's all any of us can do. Take our best shot at understanding the universe, calculate what our understanding predicts, and see if nature agrees. When it does, when the prediction matches experiment to 9 decimal places, you know you've understood something real, something true about how the world is built. That's the only validation that matters. Not Einstein's respect, though I won't deny I was pleased to have earned it, but nature's respect, earned through successful prediction. That's what physics is about. Everything else is just conversation.